Okay. Hello, everyone. So, guys, as we know, GATE Aerospace 2023 happened on 11th, and now the response sheets are out. And for the entire question paper, I have already posted the keys corresponding to the main question paper, what we have available on the website. So, as of now, in this particular video, I'll be talking about the propulsion part solution, and similarly, different videos will be uploaded for structures, flight mechanics, aerodynamics, space mechanics, which is a heavy topic this year, and then aptitude, maths, fluid mechanics portion. So as of now, I'll try to focus on only on propulsion part. For the entire 65 questions, you can refer the key on the website. I've already uploaded the PDF along with the keys. So without wasting much time, I'll move ahead. So as per the feedback received from students, 2023 was more of a conceptual paper. It is having more MSQs and more theory questions, very less numericals compared to previous years. So we'll see what happens in propulsion. So I've segregated the topics in propulsion. If you see, there are almost equal distribution. So if I say 1 mark and 2 mark, right? And these 4 topics which were asked in your exam. So there is no axial flow turbine numerical asked in this particular year, 2023. But if you see in compressor, axial flow compressor, there is one 1 mark question. Then in jet propulsion, which is heavy topic always, it's a favorite topic of propulsion syllabus. So 4 1 mark question and 2 2 mark questions. So we can see the marks also here on the right hand side. Similarly, rocket, we have 2 questions from 2 marks, and then centrifugal 1 question of 2 marks. So total weightage of propulsion is 15, which is perfectly distributed. Every year we say propulsion weightage is around 15 marks. So seeing these numericals, I have already pulled out the numericals coming in your exam. So it started with question number 20. All right. This is a MCQ question. This is asked for 1 mark in this exam. Let's see the solution. So they're saying there is a single spool aviation turbojet engine. So we are talking about specifically a turbojet engine. Which of the following statement is the correct relationship? Is the correct relationship between the total work output WT of a 2-stage turbine and total work required by a 6-stage axial compressor, neglecting losses? So in broadly sense, they are asking what is the relation between compressor work which is being supplied by turbine. So if I don't go in detail much. So if you talk about turbojet engine, right, this is basically a schematic diagram. So you have a compressor which is mounted on a shaft, and you have a turbine on this stage. So when this turbine rotates, this shaft rotates, and hence this compressor rotates. All right. And if you see the basic principle, right, if you see even closely the schematic diagram, you see compressor I have made thicker, correct, in width in this schematic diagram, just to show. Whereas in turbine, I have shown a very thin section. This is nothing but our turbine. And if you see, it's very thin compared to compressor. The reason being, compressor always has multi-stages because it operates under adverse pressure gradient, whereas turbine will produce work easily because it works under favorable pressure gradient. Now, what is adverse and favorable? In compressor, you enter at, let's say, 1 bar, and you exit at 5 bar, and it is always difficult for you to move from 1 bar to 5 bar, and hence you have more stages to do this slowly and slowly. There is beautiful theory related to this. I'm not going into detail for this numerical. In turbine, you do expansion, right? So let's start with 5 bar and go to 3 bar, and this is known as favorable. 5 bar to 3 bar, it is always easy to move. But in compressor, 1 bar to 5 bar, nature doesn't allow this, and it is very difficult to move from low pressure to high pressure. This is the reason compressor has more stages, turbine has less stages. Now, the question says, what is the relation between this 2-stage turbine and a 6-stage compressor? So as a total work, no, simple theory on which turbojet engine operates, turbine work should be equals to compressor work. Anyhow, we are neglecting losses, so there is no mechanical efficiency, no transmission efficiency considered. So turbine should produce the work which is exactly needed by compressor. So if your turbine is producing, let's say, 10 kilowatt of power, which we say as, if you multiply with mass flow rate, you will get power. This 10 kilowatt if we assume there are no losses, should be supplied exactly to compressor. We should not produce more energy, and the remaining energy, whatever you have after this, should go to nozzle in which you will produce high velocities. So turbojet engine backbone, once you go through the entire lecture of jet propulsion, right? This is the major difference between turbojet engine and let's say turboprop. In turboprop engines, where you have big propeller blades, all right, outside the cowling, you have a compressor, you have a turbine. In this, turbine work is to drive compressor and this propeller blades also. So it is not, turbine is not equals to compressor in this case. Turbojet engine, on the other hand, works on this basic principle that whatever work you're producing in turbine should be supplied to compressor. That's it. Otherwise, don't waste your energy. Give it to nozzle as much as possible. So option for this is option C. I'll move ahead. This is asked for 1 mark, MCQ. All right. Question number 2. Again, asked for 1 mark. Question number 21. All right. Let's see this. In a stage from an 50% reaction ideal flow compressor. So you're talking about AFC now, 50% degree of reaction. R is equals to 1 by 2. Now, what is the meaning of this R equals to 1 by 2? The basic definition says how much, you know what a compressor is, right? The compressor has a rotor blade and has a stator blade, correct? And you install blades in this. You have rotor blades installed and then you have stator blades installed. I'm again not going into theory of velocity triangles and all, not needed for this numerical. But when we say degree of reaction, right, its basic definition is how much static enthalpy rise. I'll write this definition. The definition, if you open any book, study material books, any textbooks, the definition says this: static enthalpy rise in rotor compared to static enthalpy rise in stage. Now, you know what a stage is, right? Stage is a combination of rotor and stator. This is a complete stage. So if you see this ratio as 1 by 2, meaning if this ratio is 1 by 2 means if rotor is, if total rise is 2, out of which rotor is doing half of it. 1 by 2 means rotor is contributing half of stage. Now, if you see all the options, right? Stagnation, static enthalpy rise across the rotor is 50% of the rise across the stage. That's what the meaning of degree of reaction is. If you see other options, right, that is altogether wrong. Axial flow component of velocity always remains constant. 50% rise of the stator. They have given this to confuse you. Stagnation enthalpy, we never talk about this. So basic definition in any textbook, if you open, or any lecture you listen, or any material books you read, right, the first definition for degree of reaction starts with this for compressor. So option B. All right, I'll move on to next numerical. Again, this is first I'm doing in sequence, so all are 1 mark questions now. So this is question number 22. Let's read about this now. An aircraft is cruising with a forward speed of VA. So you have an aircraft. I'm talking about propulsion, so I'm drawing just only engine. So when your aircraft move forwards, air enters inside this with a velocity of VA. This first statement. And the jet exhaust, that means the velocities which are coming out from the engine relative to the engine at the exit is VJ. So at the entry, your velocity is VA. At the exit, the gases which are coming out, its velocity is VJ, and they have given certain ratio, which is VJ by VA is 2. What is the propulsive efficiency? Now, this is very formula-based, very gifted question. When I say propulsive efficiency, right, it is defined as 2 alpha divided by 1 plus alpha. Now, in this alpha, this is the important thing, is nothing but velocity at the entry divided by velocity at the exit. Speed of air divided by jet speed. In this, they have given us the ratio which is opposite. That means they have given this as 1 by 2. So if I'll substitute this 1 by 2 value here and solve this, you will get this value as 0.67. I already have the numbers, so I'm just quickly writing this, not showing you the calculations. So its efficiency simply becomes 0.67. It is an MCQ. Multiple choice question, so simply you need to mark the option. So we have seen 3 1-mark question number 20, question number 21, question number 22. I'll move on to next. This is question number 28 now. And if you see, this is multiple select question. So you need to read all the options very properly. Let's see this. From the options given, select all that are true, and hence it becomes multiple select for turbofan engine with afterburners. And you know what afterburner is. Afterburner is used to produce high thrust for short duration of time. It's basically a thrust augmentation process. All right, to produce very high amount of thrust for a short duration. All right, so let's read the topics options now. Turning afterburner on increases specific fuel consumption. Definitely, when you burn more fuel, then only you'll going to get more thrust, right? That's what the main function of afterburner is. So afterburner is basically installed after turbine, because you don't want to spoil your turbine blades because of high heat, high temperatures. So afterburner, when it is turned on, you burn huge amount of fuel and produce thrust. This is used typically in aircraft applications at the time of takeoff, or during fighter aircrafts. If you are, let's say, in enemy territory and you want to run faster, you want to do some very high maneuvers, you want to produce high thrust, so you use afterburners. So definitely, I'm not worried about fuel consumption at that point. So fuel consumption will definitely be high if I turn on my afterburner. Next, after turbofan engines with afterburner have variable area nozzles. Now, this is might be tricky for people, those who have not studied a complete theory of jet propulsion, but this statement is correct. The reason being, once you use afterburners, right, you're increasing your temperature to very high value. Correct? When your temperature increases to, yes, correct. Yes, correct. So when your temperature increases to very high value, there is huge density variations. All right, now what is density variations? I'll take it very simple. You know, P equals to rho RT. We have ideal gas equation, right? I'm just trying to give you an explanation which is very simple and short. If, because we know in turbofan engines, we add heat at constant pressure. We don't want to change pressure. That's what Brayton cycle is. If this term remains constant and this temperature increases, this density has to come down. All right. Now, when density is low, the problem is mass flow rate we know is conserved, right? Mass flow rate should remain constant, which is rho AV. Now, if density is decreasing because of this high temperatures, then to compensate for this, area should increase. This is one very simple, very crude explanation. Let me give you one more explanation. So area should be increased, and hence we use variable area nozzles. The second problem is, if you have an engine and you have used afterburner here, let's say this is your afterburner. After this, you have a nozzle. All right. This nozzle has a throat, right? And the gases need to come out from this throat. Correct? Now, when we say high temperature, we say less density. Less density means you're talking about taking more volume. Correct? Density we know is nothing but mass divided by volume, right? Correct? So volume is more. That means it is very difficult for my air or my gases to come out from the smaller area. So what we do in real applications, we increase this throat area a bit. This is known as variable area nozzle. So to prevent choking, this is one very important measure to prevent choking, not in turbofan, in any engine. We typically use variable area nozzles. So when we have afterburners, we have to use it. Otherwise, there will be choking phenomena, which will lead to very reverse flow and may destroy our whole engine. Now, if I'll come to option C, turning afterburner on decreases specific fuel consumption. Definitely it is wrong. And increases stagnation pressure across the engine. Turning afterburner on increases stagnation pressure across the engine. Definitely no. Whichever engine we talk about, turbojet, turbofan, entire gas turbine engine family operates on heat addition at constant pressure. Correct? So pressure should remain constant, and we name in thermodynamic this as Brayton cycle. So option C and D doesn't make sense, and option A and B are correct here. I'll move ahead. Question number 35. This is numerical answer type. This is asked for 1 mark. So fill in the blank. We need to calculate this. All right. I try to keep it as simple as possible. A supersonic vehicle powered by a ramjet engine is cruising at a speed of 10,000 meter per second. So I always have a tendency of drawing the schematic diagrams. So when your ramjet engine is moving at 1,000 meter per second, means air at the entry, which we denote it as CI or CA, that depends upon nomenclature, enters at 1,000 meter per second. All right. The ramjet engine burns hydrogen in a subsonic combustor to produce thrust. So in combustion chamber, let's say this is your combustion chamber, you're burning certain propellant, they're saying hydrogen. All right. The heat of combustion for hydrogen is this much. So they have given one value here, that the heat of combustion. So when you burn some propellant or you burn some fuel, heat is getting produced, right? So in simple words, let's say something like this. This heat added is 120 megajoules per kg. You can see this is specific heat as per the units. The overall efficiency of the engine, which they have denoted as eta naught, it is defined as the ratio of propulsive power to the total heat release in the combustor is 40%. So I'll come to this definition in more detail. This is given as 40%. So I'm writing it as 0.40. They have given me acceleration, and they ask me what is specific impulse of this engine in seconds, round it off to nearest integer. So always when we go in detailed lectures, right, I always have a habit, or I always insist people or students to understand this way. Just see what you want to calculate in the end first. You want to calculate specific impulse, correct? From basic, you should know that specific impulse is nothing but Cj divided by G. So if I know Cj, anyhow, gravity is provided in the numerical. If I know Cj, I get to this numerical 1 mark, correct? And this should be in seconds. So the only thing is I need to calculate Cj. For this, they have given me overall efficiency. Now, again, if you open any textbook, you should know that overall efficiency is nothing but this propulsive power, which is thrust into Ci divided by heat power. That's what they have given. I've just written formula here for this. They have given defined as the ratio of propulsive power to total heat release in the combustor. Now, everyone knows what is thrust. This is m dot A into Cj minus Ci into Ci divided by our heat power. Correct. Now, the thing is, they have given me heat power in specific. That means I don't want kilowatt. So what we'll do is, guys, please try to understand this. And any doubts, I'm always open. Whatever you have, please let me know. I'll try to clear your doubts. This m dot A, I'm taking to denominators. Then this becomes kilojoules per or joules per kg. That means specific heat. So ideally speaking, my formula becomes this: Cj minus Ci into Ci divided by heat power divided by mass flow rate, which is given to me as 120 into 10 to the power 6. This is given as 0.40. I know Ci, which is 1000. You can substitute everything in this and calculate the velocity Cj. Now, once you know this velocity Cj, we know how to calculate ISP. What you can do is, I have already calculated this, so I'm not showing you the calculations. But ideally speaking, this is Cj. This Ci is given as 1000. This Ci is given as 1000 divided by, I have converted this into SI units. This is given in megajoules per kg. So I have multiplied with 10 to the power 6. You solve this, you will get this as somewhere around 47,000 meter per second. Now, if I take this value and substitute here, which is 47,000 divided by, they ask me to calculate gravity, take gravity as 10, and you will get this as 4,700 seconds, which is asked in the numerical. Round it off to nearest integer. We are already getting this as a perfect integer. So the key for this becomes 4,700. This is asked for 1 mark. People feel that this is lengthy question, but without explanations, if you know this right, it should not take more than 2 minutes to solve this numerical. This is question number 35. So there are 5 questions asked for 1 mark. So we have covered these 5 questions now. I'll move on to next. This is question number 38. Now we are entering into 2-mark questions. This is multiple choice question asked for 2 marks. It's from rocket propulsion. Please listen to this. I'll try to again keep it simple. 2 missiles, A and B. So there are 2 missiles, A and B, powered by a solid rocket motor having identical specific impulse. So let's say this rocket has specific impulse of ISP and ISP. This is similar, so I've written it. Lift-off mass of 5,600 kg each. So both these rocket motors, have same mass when they are starting. So let's say initial mass I'm denoting as M1. This is 5,600 kg. This is also M1. This is also 5,600 kg for both. The burn duration TA is 30 seconds and TB is 70 seconds respectively. So for rocket A, burn duration means the time you will going to burn propellant. So in rocket A, we are burning propellant for 30 seconds. Whereas for rocket B, we are burning it for 70 seconds. Right? The propellant mass flow rates M dot A and M dot B for missiles A and B respectively are given as this. So for missile A or for rocket A, you are burning this much amount of propellant. Whereas for B, you are burning this much amount of propellant. So guys, as of now, I have not done anything fancy here. Please don't get confused in this. This is very straightforward. What they have done is they have given me 2 rockets and they have said same impulse, same weight or same mass. And then the only difference is amount of propellant burned and the time period for which you are burning. So 2 rocket motors are different in burning propellant. That's it. Now the statement is neglect gravity and aerodynamic forces. The relationship between the final velocity VA and VB of missiles A and B respectively is given by. In simple words, what is the velocity of rocket A and rocket B when this is the only difference? Now the backbone of whole rocket unit is nothing but the rocket equation, which is basically given as, I'm using the same terminology what they have provided. So velocity is given as ISP into G into ln of M1 by M2 minus G into TP. So I have not taken any assumption in this. This is the entire or complete rocket equation. Now, first statement is neglect gravity. So this part goes to 0. Gravity losses should not be considered. All right, don't neglect this G. Only losses are neglected. So we have this ISP G ln of M1 by M2, where M1 is the initial mass of the rocket and M2 is the final mass of the rocket after burning the propellant. All right. Now, what I'm going to do is for both these rockets, I will first calculate what is the mass of that particular rocket after burning propellant, meaning I will be calculating M2. I'll again repeat this. What is M2, guys? M2 is nothing but what is the total mass when you're starting your rocket minus when you have burned your entire propellant. That is nothing but remaining mass. I'll use this for both rockets. Now, if you see, I need mass. What they have given me? They have given me mass flow rate, but they have given me time period also. I'm going to next slide to show you this. Let's do left-hand side for rocket A. So the mass of propellant for rocket A is nothing but you are burning 120 every second and you are burning it for 30 seconds. So 120 into 30. This is nothing but 3,600 kg of propellant burned for rocket A. Rocket B, let's say propellant for B. Every second you're burning 70 kg and you're doing this for 70 seconds. So this becomes 4,900 kg. So we have both the masses of propellant burned. This should not be used in the equation. M2 is the difference. So what is M2 for rocket A? Initial mass minus the propellant mass. I hope it is clear. This is 2000. This is M2 for rocket A. This is M2 for rocket B. Initial mass is same for both the rockets, but propellant mass is different, and hence the final mass came out to be 700. Now I know M2 for both the rockets. You know what we need to do. We need to get a relation between VA and VB, right? So I'll simply take the ratio. Velocity of A divided by velocity of B is nothing but ISP into G into ln of 5600 divided by M2 for first rocket. This entire term divided by ISP into G into ln of 5600 divided by this. This is very simple calculations once you understood the concept. Same impulse, gravity remains same. You solve this, you will get this relation directly as 0.5 into VB. So velocity of rocket A is half of velocity of B, which is one of the option C. If you're looking for this for the first time, then definitely it might look slightly tricky, but in rocket propulsion, when we do this, we derive this equation, and there are like more than 50 numericals we solve on this concept. So I hope this is a repeated question from our books, from your test series, and from the lectures itself, videos. We have solved many numericals of this sort. I'll go to next. Question number 41. Now again, seeing this, people have a fear that I don't know what they're doing, scramjet engine and all. I'll stick to the basics. A scramjet engine features an intake, isolator, combustor, and a nozzle as shown. So if you see, this is intake, isolator, combustor, nozzle as shown in the schematic. Section 3 represents the combustion entry point. So here we are entering into combustion chamber. Assuming stagnation enthalpy. Now, this is what I want you people to understand properly. Assume stagnation enthalpy to be constant between station 1 and 3. So station 1 and station 3, stagnation enthalpy remains constant. So meaning the only data they have given me numerical is stagnation enthalpy at 1 and 3 remain same. As simple as that. Nothing bad. Whatever they have given, I have just written that. And air to be excuse me, and air to be calorifically perfect with specific heat ratio as gamma. Fine. The correct expression for the Mach number. Now, if you see, it looks really bad, right? If you see options, they have given me scramjet engine, blah, blah, blah. So I'll try to keep it simple. If something like this happens, how to approach this numerical? You see all the options. These are in terms of Mach number. And if you see, these are in terms of temperatures also. Correct. Now, what I should do is I should write my equations in the same form. So guys, you know what is enthalpy, right? Enthalpy, stagnation enthalpy is nothing but Cp T01. It is equals to Cp T03. The Cp got cancelled out. Correct? So we have T01 equals to T03. Very simple expression. Now what I'll do is I'll again try to break this in terms of static temperatures and Mach numbers. We know how to do it. This can be written as T1. And 1, if you see, these are infinity, right? M infinity, T infinity, P infinity. So I'll try to follow same. Concept here. So this is T infinity plus V infinity square divided by 2Cp. That means you can write it as T infinity or T1. It's one and the same thing. This is nothing but T3 plus V3 square by 2Cp. You know what Cp is, right? Gamma R upon gamma minus 1. Now what I'm doing is, don't forget, you need M3 equals to something. And what is M3? M3 is nothing but velocity at 3 divided by speed of sound at 3. So I try to form these terms. So what I'll do is, I'll divide this entire equation with T infinity first. So what this becomes? This becomes 1 plus, I'm skipping one step here, assuming that you are already done with the basics. So you are looking for the solution of this. This becomes gamma minus 1 by 2, V infinity squared divided by gamma R T infinity. You can check. I've simply written Cp as gamma r upon gamma minus 1. This Cp is written as gamma r upon gamma minus 1. And I've divided by T infinity so that I can form Mach numbers equals to, on this end, this becomes T3 by T infinity plus V3 square. Let's write this also. So this is gamma minus 1 divided by 2, right? V3 squared divided by gamma RT infinity. Now the thing is this side is making real sense. 1 plus gamma minus 1 by 2 m infinity square. This is fine. Equals to T3 by T infinity plus gamma minus 1 by 2. Now the problem is, this is gamma RT infinity. I don't want this. I want T3 here. Correct? So what I'll do, I'll multiply and divide by T3. Correct? So what this becomes, T3 divided by T infinity. And we are left out with V3 square divided by gamma RT3. Now, this need not to be learned. No one will learn this. At least no one in my batch will learn this, because you should see which option makes sense here. Actually, in your exams, you already got 2 marks, because if you see in your derivation, you're getting this term, right? Out of all the 4 options, only option B is what having this term. You can check here, 1 plus gamma minus 1 by 2 m infinity square. But I will derive this completely. So this is m3 square, Mach number, velocity divided by speed of sound square. So let me, okay, I have not given space for this. Let me write it here. So what this becomes, guys, 1 plus gamma minus 1 by 2 m infinity square equals to T3 by T infinity. I'm just copying this. T3 by T infinity, sorry, plus gamma minus 1 by 2 T3 by T infinity into M3 square. You can check here, guys. T3 by T infinity gamma plus 1 by 2. And this part I've written as M3 square. Now, again, why I'm doing it? Because I want my option in terms of M3 and M. So I've written everything in terms of M and M3. And then I'll simply send things. Now, what is M3? Okay, let me not skip any step. So you can take T3 by T infinity outside. This becomes 1 plus gamma minus 1 by 2 M3 square. Now from this, you just need to calculate M3 value. I hope you understand. You cross multiply these values. So what this becomes, 1 plus gamma minus 1 by 2 M infinity square multiplied with these values. Then you send 1 to other end. All right. And then you multiply this expression with 2 upon gamma minus 1 under root. This becomes my M3. I know I'm bit fast in this, but when we go in detailed of jet propulsion and all these things, right, you should, this is the reason we are saying this is conceptual paper. So they just want to see whether you know the concept or not. It's kind of a derivation which they have asked. I already told you in your GATE exam, just writing these 2 statements itself tell me that my option is B. But still, because I want to give you complete solution, I have simply sent the other terms and I have derived the complete expression, which is shown as this for M3. This is question number 41, asked for 2 marks. I hope it is clear. Now only 2 questions left. Let's quickly finish this, and which sums up, no, 3 questions. So which sums up to our complete propulsion solutions. Let's come to question number 61. So this is related to combustion chamber. All right. Now, this is very much repetitive. They have given ethanol. They have given different fuels in the previous year examinations. Let's read this. A gas turbine combustor is burning methane. Now, methane is asked for first time. So you are burning methane and air. So this is fuel. This is air. And you are burning it at an equivalence ratio of 0.5. And they have given me the theory also. Equivalence ratio is nothing but fuel to air ratio, which is actual. Actual means which is happening inside your combustion chamber when you're flying. and fuel to air ratio, which is stoichiometric. Ideally speaking, this is when you're doing decided in your lab. So this denominator is an ideal case, which you want. Actual is which is happening in the real life when your aircraft is flying. This is ratio is known as equivalence ratio. All right. If the ratio of mass flow rate of fuel to the mass flow rate of air is stoichiometric, that's what they have given. We know this. If the airflow is 20 kg per second, then the mass flow rate of methane is what? That's what they have asked. Now, maybe it is clear. If not, let me explain this. So first of all, I have equivalence ratio, correct? I have air and I need to calculate mass flow rate of methane. So you have air in numerator. You want to calculate fuel, which is asked in the numerical for 2 marks. So I should know my denominator, right? And we know this from theory. I have solved more than 20 numericals on this concept. Schematic is calculated from combustion chamber chemical equations. Now, what you're burning? You're burning methane. Methane is CH4. This we definitely need to know. So they have given ethanol, methanol in the previous year examinations. They have given methane now, and you are burning air. Now, the thing is, when you burn air, right? Air is oxygen and nitrogen comes along with it. This is the important part. So when nitrogen comes along with it, the actual, if you open any class 10 plus 2 chemistry books, right, they will use something like this. 4 times of nitrogen. So ideally speaking, it is not actually. What is the meaning of this? 25% of oxygen and around 75% of nitrogen, which is not the case. It is not the ratio. So one oxygen molecule comes with 3.76 times of nitrogen. This is the ratio of our atmospheres. All right. This is the actual ratio of our atmosphere. So oxygen doesn't come alone. Oxygen comes with nitrogen. That's what we say as air, which is present in our atmospheres. So this ratio is not straightforward. But one thing, when any of this numerical comes, and I've stressed a lot in my lectures, in my materials, everywhere, that when you do stoichiometric reaction, right, meaning I want complete combustion. What is complete combustion? My combustion product should be carbon dioxide and it should be steam, and I should have nascent nitrogen. Means nitrogen should not mix with any of carbon or any component. The reason being, I'm just giving an example. If this nitrogen mixes with nitrogen, if this oxygen mixes with nitrogen here, so this is carbon monoxide, which is poisonous. This is nitrogen monoxide, which is poisonous. Your aircraft will not pass emission laws, and hence you will not be allowed to fly. So complete combustion means carbon dioxide should be formed, water as in the form of steam should be formed, and nitrogen should not combine. This is the combustion which aircraft should follow. Otherwise you're not allowed to fly, because you will have poisonous emissions coming out. Then we do balance, and if you do balance, right, 1 oxygen means 4 nitrogen. Here 2 oxygen means 8 nitrogen. I'm again saying this is theoretical. This is very precise. This is theoretical value. Ideally speaking, actually, this should be 3.76 into 2 times of nitrogen moles compared to 2 oxygen. Now, if you balance both sides, you will get something like this. 3.76 into 2. If you don't like this, I'll just keep it simple. You will do this perfectly when you're preparing this. I'm saying simply this, so that I can ease my calculations a bit. I will not do this in my GATE exam. I will take it as 3.76 into 2. 3.76 into 2. But now I'll come to the main numerical, because I'll be definitely getting the correct answer here also. So this is fuel. This is air. And these are my combustion products. This is known as stoichiometric chemical reaction, meaning, simple words, you are doing this in your lab, and this is how combustion should happen. Now, if you want to calculate fuel to air ratio, I'll simply do these calculations. Fuel to air ratio, according to my chemical reaction, should be weight of fuel divided by weight of air. Now, what is fuel? Fuel is CH4, right? One carbon atom whose atomic weight is 12 plus 4 hydrogen atom whose atomic weight is 1. So carbon atomic weight is 12, hydrogen is 1, and nitrogen is 14. You should remember this. Divided by air. Now, air is 2 oxygen molecules. Oxygen is 16. So 1 oxygen is 16, 2 is 32, and you have 2 moles of it. Plus you have 8 nitrogen moles, and 2 atomic weight is 14, so it will be 28. If I'm doing this with assumption with 4 here, 4 into 2. So 1 oxygen comes with 4 nitrogen. That's what I'm assuming. Ideally speaking, actual number is 3.76. I hope this is clear. Once you solve this, you will get your schematic ratio as 0.056. All right. Now I'll come to my numerical. What is my final numerical? Equivalence ratio, which is given as 0.5. In this, what is actual fuel mass if my air is 20 kg per second divided by fuel to air ratio, which is quitometric, which is 0.056. You solve this, you will get the answer as 0.56 kg per second. You can try out your calculations. Anywhere you have a small doubt, again, this is only preparing the solutions, guys. This is not actual lecture. Actual lecture will be very much detailed, explaining what is carbon, what is atomic weight, what is molecular weight, what is number of moles. And we have more than 10, 12 questions exactly on same concept in the previous year itself. So this is not a new question coming in 2023. This is exactly copy pasted. The only thing they have done new here is they have changed fuel, which was not done before. They have used methanol and ethanol in the previous years. They have used methane here to check whether you know the basic concepts. If this part is clear, I'll move on to next numerical. This is asking, again, same question number 64. This is asked for 2 marks, numerical answer type. So this is related to centrifugal flow compressor. All right. Now let's read the data. A centrifugal A compressor has inlet root diameter and outlet root diameter of impeller as this. So impeller entry, you know the notations. Entry I'll say as 1. Exit I'll say as 0.6. So impeller diameter at the entry and at the exit came out to be this much. Fine. The pressure ratio is 5. So pressure ratio of this compressor is given as 5. Air at the inlet of rotor is 1 atm and 25 degrees Celsius. So they have given me pressure at inlet given as 1 atm, and they have given me temperature to 25 degrees Celsius means 273 plus 25, which is 298 Kelvin. Now comes the important part. The polytropic efficiency is 0.8. So polytropic efficiency of this compressor is 0.8. Typically, I've seen people missing polytropic efficiency in theory. They always focus on isentropic efficiency, but this is an important relation, guys. And slip factor is 0.92. Let's say slip factor is 0.92, denoted as mu. Cp is given, gamma is given. Now, the final question is, what is impeller speed in revolutions? This is the major task, right? Whenever any numerical comes, not only in propulsion, in any topic, you should know what you want to calculate and whether you have data for it or not. Impeller speed in revolutions per minute, meaning simple words, they're asking what is N? Fill in the blank in RPM, round it off to nearest integer. Now, everyone knows if you want to calculate N, you should know U, impeller speed, pi dN divided by 60. So to get 2 marks in my GATE exam, I need N. For N, I know diameter D2, I know pi, I know 60. So the only numerical or the hard work you need to do now is to calculate U2. And now see what they have given. I have polytropic efficiency, I have mu, I have pressure ratio. So I'll try to relate the data. So how to use polytropic efficiency first of all. All right. So simple relation. I'm not deriving this because this is not scope of this lecture. T02 by T01, which is temperature at the entry and exit, is equals to P02 by P01. Now, if it is an isentropic process, right, simple relation is gamma minus 1 by gamma. But now, if you have polytropic efficiency, this I have derived in my lectures. So as of now, I'm directly using the formula. So you have polytropic efficiency. Now, if you see, you know P02 by P01, which is 5. You know what is gamma. This is given as 1.4 gamma polytropic efficiency. T02 divided by T01 is 298, meaning you can simply solve this equation and calculate T02, which I have solved. So I'm just simply substituting and calculating this number. I have T02. Now, the last point for this numerical is once you know T02, temperature change across compressor, which is basically T02 minus T01, is basically mu into U2 squared divided by Cp. Now, if you have studied compressor, centrifugal flow compressor with me, you should know this. Everyone should know this. Now, what I'm trying to show here is, you know this difference, T02 minus T01. You know what is mu. You know what is Cp. You can substitute everything in this numerical. Proper units you need to follow. So let me do it here. So temperature difference is 529.48 minus 298. So you have this as 231.48. Mu is 0.92. I'll calculate U2 squared divided by Cp as 1. This is in kilojoules per kg Kelvin. So I've multiplied with 10 to the power 3. You solve it, you'll get U2. I have somewhere around this. And once you substitute this U2 here, you know U2, you know pi, you know D2, you know 60, you can calculate for N. I am getting this value as 16006 RPM, and they are asking me in integer, so I have written this. Something closer to this here and there because of some rounding of errors, but you will be definitely inside the range. Once the key is released, we can really match this. So centrifugal flow compressor, they have asked this before also. They have asked RPM of centrifugal flow compressor in previous years. So this is actually a numerical asked before. This is not new. Slip factor, mostly all gate numericals, they have given us this. But first time in centrifugal flow compressor, they have given us the polytropic efficiency. They have given us an axial flow compressor, but now first time in centrifugal, they have given this. So anyhow, this formula is same for axial flow, centrifugal flow. Any compressor, the formula remains same, which we have derived in our previous lectures. I'll go to the last numerical, which is asked in 2023. Very simple, straightforward question. But still, I've seen in the response sheet, mostly people are struggling in this, but this is very straightforward, guys. But again, this is related to combustion. Let me read this. Consider a cryogenic liquid rocket engine using an expander cycle with liquid hydrogen and liquid oxygen as two propellants. Now, guys, it's a cryogenic rocket. It is using liquid hydrogen and liquid oxygen as two propellants. You know, in rockets, we use propellant, right? In the previous numerical, it was solid rocket motor. Now it is cryogenic rocket. So you're using liquid hydrogen and liquid oxygen as two propellants. The mass flow rate of hydrogen in the combustion chamber is this. So I'm simply writing it. Mass flow rate of hydrogen is given as 32 kg per second. And the mass flow rate of oxygen is into the chamber is this. So they have given me the ratio. They have not given me the direct value. Oxygen to hydrogen are given in the ratio of 8. You know what is hydrogen, right? 32. So you know what is mass flow rate of oxygen. 32 into 8, which is 256 kg per second. Although this data is not needed, you will come to know later, but I've just written the data so that you feel comfortable. The combustion of hydrogen and oxygen is kytometric. You know what is kytometric, right? Ideal, laboratory, perfect combustion products. Now, I'll simply write the chemical equation. So you are burning liquid hydrogen with liquid nitrogen, oxygen. And we know one thing for sure, that once you have stoichiometric means, your combustion product should be perfect. That means I should get H2O, which is water or basically steam. Now, if I'll balance both these terms, right, I hope you understand this. So the combustion equation, see guys, I'll repeat this again. Hydrogen is this, it is burned with oxygen. One thing I know that I should get, which is non-poisonous. So H2O, water or steam, is non-poisonous, right? Now, if you see on the right-hand side, you have only one oxygen. But on the left-hand side, you have two oxygen atoms, right? O2. So what I'll do, I'll multiply it by 2. But now, if you see, hydrogen becomes 4 on right-hand side. So I'll simply multiply it by 2. Plus, energy will be released. Now, what they're asking in the exam, I'll explain this meaning of energy. Now, what they're asking is, assuming the rate of forward reaction is much larger than the reverse reaction, anyhow, we never consider reverse reactions. The rate of formation of H2O is, at what rate H2O is formed? You know, H2O is formed here as 2, right? That's what they're asking. The rate of formation of H2O. Now, what is the meaning of this energy, guys? This energy, when you burn hydrogen, hydrogen reacts explosively with oxygen to form water. That's what you have seen. Hydrogen reacts with oxygen to form water. This reaction, when these two things are mixed together and ignited, right, they will form huge amount of energy. And this along with definitely steam. All right. This huge amount of energy along with heat, this will expand in the engine nozzle and they will come out from the nozzle at very high speeds. Typically, I've taken this from NASA PDF. This is around 10,000 miles per hour exit velocity, which is CJ. And this fast moving CJ will produce thrust in the forward direction. That's what the main motive of any combustion, right? To produce thrust in the forward direction. So I'll simply say this, as per this numerical answer for this is 2. That's what they're asking, rate of formation of H2O, which is 2 here. This energy is formed, which is because of burning of these oxygen and liquid hydrogen. This is all they have asked in 2023 related to propulsion. I already told you this before. They have asked 10 questions, 5 questions of 1 mark, 5 questions of 2 marks. You can see this is 1 mark, this is 1 mark, and then this 2. This is basically this. So we have 5 1 mark questions and we have 5 2 mark questions, which total sums up to 15 marks. We have solved these 10 numericals. You can verify the keys for this. And if you have any doubt, feel free. I have already mentioned my contact details. So you can feel free, you can WhatsApp me, you can give me a call, and then you can verify the key. Although it is not relevant here in this numerical, but this is just to tell that admissions are open for 2024. Feel free to message me or call me for any doubts, and I can give you all the details, whatever is needed. I hope this is clear. We are fine in this, so I'll wrap it up and maybe I'll see you in the next lecture related to some other topic. Thank you so much, guys. Bye-bye. Take care.